So now let's look at composite functions. What are composite functions? Composite functions combine two relationships into one function. And I'm betting that you've seen examples of this before. Let's see. What if I let f of x equal x plus 5? I'm just making that up. And what if I let g of x equal 2x to the second power minus 4? A composite function would say, what is f of g of x? And in order to answer that question, what is f of g of x, you would first have to figure out what is g of x. And so we would take, in the place of the g of x that we defined as 2x squared minus 4, we would put that into the position of g of x because they really are equal, so they can be substituted for one another. And then we would take 2x squared minus 4 as our new input of the f function, and so this would become 2x squared minus 4 plus 5. In other words, this x that was x plus 5, really you should think of it as an input plus 5. So my input is 2x squared minus 4, still plus 5. And if I can combine like terms, I will. So I would get 2x squared plus 1. And that is what a composition of functions is. Now, an interesting thing happens when you compose a function and its inverse, or an inverse with a function. For all inputs of the corresponding domain, the result is the original input. In other words, if you have f of f inverse of x, then you're going to output x. In other words, whatever is your input becomes your output. And if you reverse that, if you take f inverse of f of x, you will also equal x. That is a characteristic of a function and its inverse. So for trigonometric functions, if you have sine of sine inverse of x, we can still expect x. Of course, we are on a limited input. And if we reverse that and do sine inverse of sine of x, we are on a limited input as well. You can go through this list for the rest of them. For cosine, cosine of cosine inverse of x will be x for our input of -1 to 1. And for the inverse composition, we are on a limited input of 0 to pi. And then finally for tangent, tangent of tangent inverse of x is equal to x for all real numbers. And then if we reverse that, we are on a limited domain of -pi over 2 to pi over 2. So what I have circled is a nice reminder of what the restrictions are on the function in order for this to be 1-to-1. So let's look at an example. Evaluate the following. And notice over on the right, I have included what we just showed, the composition of trig functions and its inverse. And I've also included a unit circle because a lot of times we can get these answers by just looking at the unit circle. So the first one says sine inverse of sine of pi over 3. So what we saw with a function and its inverse on the previous slide, we said in words that a function and its inverse, that whatever the input is, the output is as well. So what I'd really like to say is that this is equal to pi over 3. The way I think of it is that an inverse undoes the sine. Now, there is a restriction on this. I have to make sure that that answer of pi over 3 for the sine is within my restricted domain. So this was a sine inverse of sine. So that matches with this fourth statement. So I can only make that statement about pi over 3 if pi over 3 is between pi over 2 and negative pi over 2. And since it is, then I am good to go. How about B? Sine inverse of sine of 2 pi over 3. So my answer is 2 pi over 3 if 2 pi over 3 for the sine function is between pi over 2 and negative pi over 2. Now, in this case, 2 pi over 3 actually breaks through the wall that, where is it at? 2 pi over 3 is right here. It breaks through that wall, and so I've got myself a problem. What I have to do, I'm going to go ahead and cross this out, what I have to do is rewrite 2 pi over 3 so that we have the same output. In other words, I can see on my unit circle that the sine of 2 pi over 3 is root 3 over 2. Is there another angle that produces the sine of 2 pi over 3 but is within my restricted domain? And the answer is yes. I can see that in the first quadrant that pi over 3 gets me the same sign. So what I'm going to say is that sine inverse of the sine of 2 pi over 3 is the same thing as sine inverse of the sine of pi over 3. That's a 3. And now, because I'm in the right quadrant, I can say that the answer is pi over 3. Part C says cosine inverse of cosine of 2 pi over 3. I'm hopeful that these two cancel out and I get an answer of 2 pi over 3, but that is only going to be the case if I am within that restriction area. So let's see, for cosine, what did we say for cosine? Cosine inverse of cosine is on this line, and it tells me that the restriction for the domain is that I have to be between 0 and pi, between 0 and pi. Where is 2 pi over 3? 2 pi over 3 is right here, and that is within that space, so that one checks. How about cosine inverse of the cosine of negative pi over 3? Is negative pi over 3 within that restricted domain? And the answer is no, because what we just saw in green is that cosine has to be between 0 and pi. And where is negative pi over 3? Negative pi over 3 is in the same location as 5 pi over 3. And that location has a cosine that is positive. In fact, it's positive 1/2. So is it possible to write the cosine of negative pi over 3 such that instead of being an angle in the fourth quadrant, I'm an angle that is in the first or the second quadrant? And the answer is yes. I can see that 5 pi over 3 and positive pi over 3, even though they're in the same, or excuse me, in different quadrants, they have the same cosine. So I can say that cosine inverse of the cosine of pi over 3 is equal to pi over 3. In other words, now I can cancel them out. And how about tangent? Tangent inverse of tangent, I am really hoping that the tangents cancel out, and that will be true if pi over 8 is in what quadrant? Well, let's see here. For the last line of this upper block, we say that tangent inverse of tangent of x is equal to x only if we are between pi over 2 and negative pi over 2. So is pi over 8 in that area? Well, if I start on the positive x-axis and I move counterclockwise, the first thing I get to on my graph is pi over 6, and then I go to pi over 4, and then I go to pi over 3. The denominators are getting smaller. Pi over 8, therefore, must be, well, it would be halfway between 0 and pi over 4, wouldn't it? So it would be about right here, just below 30 degrees or pi over 6. That's my estimate. It doesn't really matter what the exact value is. I'm just looking to make sure that pi over 8 is within that restricted domain. And it is, so I'm going to say that the answer is pi over 8. And finally, the last one, tangent inverse of tangent of 11 pi over 9. I would really like this to be true. And is it? Where is 11 pi over 9? 11 pi over 9. Let's think about this. Well, pi is 9 pi over 9. So 11 pi over 9 goes beyond that. I'm not really sure how far beyond it, but it does. What I do know is that it is not within that restricted domain. So it is not between pi over 2 and negative pi over 2. 11 pi over 9 is 2 pi over 9 units from the x-axis. So this space right here is 2 pi over 9. If I, wherever 11 pi over 9 is, if I extend that through the origin, I believe I'll have the same tangent. Now the reason for that is because the tangent, remember, comes from the sine over the cosine. So if I'm at 11 pi over 9, I would have a negative sine and I would have a negative cosine. If I go 180 degrees across into the first quadrant, I'm going to have a positive cosine and a positive sine. Same absolute values as the angle in the third quadrant. So what is that angle in the first quadrant? Well, my reference angle for 11 pi over 9 is 2 pi over 9. Remember what a reference angle is. It's the angle between the terminal side and the x-axis. So 2 pi over 9 is from the third quadrant to the x-axis, and 2 pi over 9 is going to be from the first quadrant to the x-axis. So I'm going to cross this out. I know that that's not true. And what I'm going to say instead is that tangent inverse of the tangent of 2 pi over 9 is the same thing as 11 pi over 9. And so that is my final answer. Now that we can compose a trig function with its inverse, now let's look at the composition of a function and the inverse of another trig function. Example 6. Evaluate the following. Sine inverse of the cosine of 13 pi over 6. So because sine inverse and cosine are not inverses, I can't cancel things out like I did on the previous slide. So what should I do? Well, we're always going to work from the inside out. And so I've got to determine what is the cosine of 13 pi over 6. The cosine of 13 pi over 6, let me just sketch this out real quick. 13 pi over 6, if I go all the way around, I'm at 2 pi, which is 12 pi over 6. So now I'm just going to go up to pi over 6. So what is the cosine of pi over 6? Well, the cosine of pi over 6, the cosine is the longer length, and so that is going to be root 3 over 2. And what angle produces a sine of root 3 over 2? And not only that, but it has to be, for sine inverse, it has to be between pi over 2 and negative pi over 2. The answer to that is going to be pi over 3. Make sure that you understand that. Pi over 3, of course, is right here, and I can see that this has a small cosine and the larger sine value. For b, I have cosine inverse of 4/5 on the inside, and I want the sine of that. So let's remember what's going on here. Normally, like we saw with the cosine of 13 pi over 6, normally we input an angle. In this case, I am looking for the angle that produces a cosine of 4/5. And 4/5 is not an output that's familiar to me. So I'm going to try a different technique on this one. I'm going to say, let's let cosine inverse of 4/5 equal some angle, and I'm going to call that angle theta. Well, if I take the cosine of each side, let me show you this technique. If I take the cosine of each side, 4/5 is within the limited domain that I have, I get that 4/5 is equal to the cosine of theta. Now let's remember what I did here. I said that this inside part is theta. So another way of writing the original problem is to call this, let me move up here so you can see it. Another way of writing this is to say sine of theta. And why is that? Well, because I said that cosine inverse of 4/5, I said let's let that be called theta. So I've turned it into the sine of theta. So what is the sine of theta if the cosine of theta is 4/5? Well, if we're not in a unit circle, then what we know is that the cosine comes from x over r. And we also know that x squared plus y squared equals r squared. So that gives me 4 squared plus y squared equals 5 squared. And let me just move up here. I've ran out of room. I'm going to get 16 plus y squared equals 25. Y squared equals 9. Y is equal to plus or minus the square root of 9, which is 3. And I'm going to use positive 3 so that I make sure that I'm in the right quadrant. So the sine of theta is going to equal to 3, my y value, over my r value, which is 5. So even though this looks different, because I defined theta as the cosine inverse of 4/5, I can say that this answer is also equal to 3/5.